Today we're going to be looking at Oracle, which is an easy reversing challenge from San Diego CTF 2022. This challenge is quite a bit easier than most reversing challenges, which require the usage of disassemblers such as Ghidra or IDA Pro. Since the program in question is written in Java, the quality of decompilation is quite a bit higher than if it were written in C, and we only need to really worry about understanding what the program is doing. And the flavor text reads, "An Oracle is a black box in a Turing machine. You can run it, but how do you inspect it?" We are given a compiled class file, oracle.class, which we can download and run from the command line using Java. When we do this, the program prompts us for a flag, but it will only tell us if we got it right or wrong. So to figure out what the flag is supposed to be, we will need to dig deeper. Since this is a Java program, the easiest way to get started reversing this is to just use a Java decompiler. There are some totally online decompilers that you can take advantage of. Get ready for this. javadecomplers.com. We can upload the oracle.class file, and if we leave it with the default settings, it will use the Procyon decompiler to rather straightforwardly just give us the source code of the original program, complete with variables and function names. I told you this part would be easy. On the chance this website succumbs to bit rot and no longer exists, it's very easy to go download JDGUI, which is an application that essentially does the same thing, and it should come installed on your version of Kali Linux if you're running it. Just by reading this, we can see that whatever the user inputs is first converted into bytes. Then those bytes are mutated by a series of 3 pass functions, which do a variety of scrambling operations on the input. At the end, there's a check to make sure each byte of the scrambled input matches against a hard-coded array of bytes as an output. If the 2 byte arrays match, then the input must have been the flag. This is a fairly standard reverse the encryption style reversing challenge, where this check array is essentially our encrypted flag, and we need to apply these passes in reverse order to determine the original flag. Since the decompilation is so robust, the easiest starting point is to simply copy this code into a Java file of our own. We'll call this one solve.java, and we'll make sure to change the name of the class to match. Then we'll rename this array of bytes to numbers, and we'll make it non-final, and we'll replace byte.minValue with -128. We will also get rid of the parts of this program that query for input, and we'll simply end the program by printing the contents of the numbers array. To reverse these 3 scrambling passes, the first step we need to take is to reverse the order in which they are called. Then we can look at changing each pass to undo its original operation. Starting with a 3rd pass, we can see that this pass essentially just adds a number to each byte in the array. Therefore, the easiest way to reverse this is to simply subtract that same number from each element in the array. So we'll just change this from addition to subtraction. To undo this 2nd pass, we need to make sure we understand what it's doing. This one is trickier because each element of the output is comprised of 2 different elements from the input. It's not a one-to-one mapping. Specifically, it looks like the bottom 4 bits are the top 4 bits of the original number in this index, and the top 4 bits are the bottom 4 bits of the number previous to this number in the array. There's arithmetic happening on the array index here that will always return the index before the current index in the array. If we're on the first index, it will wrap around and return the index of the last element. That is why there is modulo arithmetic in this index calculation. Okay, this is a bit difficult to talk about, so let's take a look at this small example. Imagine our byte array is only 3 bytes, and each bit is represented by a letter. The top 4 bits of the first byte, A, B, C, D, have now become the bottom 4 bits of the first byte. The same is true for IJKL and QRST. Meanwhile, the top 4 bits of the result byte are the bottom 4 bits of the previous byte. We can see that UVWX belongs to the last 4 bits all the way around in the last byte of the array. MNOP belonged to the previous byte as well, and the same with EFGH. You can think of this whole pass as just being a circular rotation of all the bits in the array 4 bits to the right. The way to undo this, then, is with a 4-bit rotation to the left. The easiest way to make this change is by simply reversing the direction of both bitwise shifts. Then we need to replace this reference to the previous entry in the byte array to the next entry in the byte array instead. That should undo the cyclical shifting. Finally, if we take a look at the first pass, we can see that this one is a bit simpler and just XORs each byte in the array by some generated value. The value itself doesn't really matter as long as we undo it. Fortunately for us, XORing is its own inverse operation, which means that if we just XOR every byte again by the same number, it should return to its original value. So we actually don't have to change anything with this first function for it to already reverse the operation. All that's left now is to run this solve.java program and see if it outputs the flag. Weirdly, though, it almost does. While some of the bytes seem close, others are definitely corrupted somehow. Our logic was correct, but unfortunately Java is just a little bit finicky about bit shifting signed bytes. Notice that the original code does this bitwise AND operation to only capture 8 bits before shifting right. We'll need to do the same on this side now that this is where the shift right is happening. So as long as we add this AND mask, it should prevent the unfortunate shifting accidents and finally should return the flag as intended.